So this week, Module 12, we're going to do an intro, and I'm going to call it a light intro because this is a very deep topic, a light intro to at-scale data development tools. So, we've done a lot of stuff, we've done a lot of programs, however, we've not dealt with very large sets of data, very high computational type tasks. And when you get into those kind of things, you run into some limitations in Python and in any programming language, frankly. But Python has these same limitations that we have the ability to work around. And two ways to go about this are using threading and multiprocessing. The two topics are similar, but kind of different. I don't know if I have an actual writing here, if I just have to say it. Okay, so I guess I don't explain what threading is and what multiprocessing is, so I'll just start with that. So threading is you have your program break into multiple concurrent processes that will run, and as they run, you can either have them output, you can have them write to a queue, you can have them communicate back to your main program in general. But what it does is it allows you to parallelize your tasks. Multiprocessing is very similar. However, with multiprocessing, you essentially create a single thread, I guess you could call it, on different CPUs in your computer. So all computers nowadays are multi-core or multi-CPU processors. And one of the things, and again, I don't talk about it. One of the things that is a somewhat significant limitation to Python is that it uses GIL, Global Interpreter Lock. And what that means is Python will only do one thing at a time. It doesn't matter how many things you attempt to have it to do, it will just do one thing at a time. So with threading, technically threading, you are not creating concurrent threads. What you are doing is you are taking and creating those concurrent processes. However, Python will do one at a time. It'll actually bounce between the different threads, but only one of them will be active at any moment. Because of that global interpreter lock, it's keeping it so it can only do one thing at a time. And there's advantages to that. It protects a lot of, it basically makes programming a lot easier because you don't have to worry about two things attempting to happen at the same time on the same piece of data and screwing something up. But it kind of, Python fakes threading, so it'll just bounce between the different threads and try to keep each one moving forward. If one's waiting on something, it'll bounce to another one, et cetera, et cetera. So threading is not necessarily concurrent. However, multiprocessing is truly concurrent, and the way it does it is it really just stands up multiple Python processes on different CPUs and allows them to run concurrently. So again, by default and by design, Python works on a single processor because when it was written 20 years ago, that's how computers were. Nowadays, of course, we all have multiprocessors. So there is a module called multiprocessing that allows you to send out tasks to the different CPUs and have them run independently, and then you can bring them back to your main program at the end. So as I finally get to what I'm saying here, threading is something that can be used when you are network bound. And by that I mean you have tasks that sit and wait on something, like a callback from an API, or a web scraping type task, or maybe you are waiting on, I don't know, a response from another system. If you thread those out into separate threads, they can all wait at the same time for responses, and then when they get the responses, your computer can very quickly take those responses and work with them. And I've got an example of that. That's a pretty good example. Multiprocessing is when you're crunching complicated, something that's just number crunching, where if you did it on a single processor, you're just going to rail your processor and have to sit and wait for it to crunch. But if you spread it across multiple processors, you can do that crunching parallel and then get your responses faster. Really, the end goal here is to speed up our program's throughput. So we're going to start with threading. Again, we'll be doing this week. We'll be doing a little bit more of it next week as well, or to wrap up the topic. But we're going to just show some intro type topics here for threading. So just a visual that I found. You know, your threads kind of work in their own independent boxes, and they interact with your data space or your main program space. I don't know how valuable that is, but I threw it in there. As I said, when you have processes that have a lot of wait time, threading can pair lots of processing. So let's actually do it. So you have to import the threading module. You do not have to install the threading module. It comes along with your base Python install. You have to bring it into your program. I'm not going to use a queue right now. I use one later. And then I'm going to be using the time module. And the reason I'm going to be using the time module is because we kind of have to force these programs to seem like they need these things. So I can use time.sleep to make processes take longer than they normally would. So it's a bit of a fake thing here, but it kind of gives you an idea of how these things work. So I've got that there. Okay, so in this example, I'm just going to create 5 threads that each print a number sent to them. And you'll see threading and multiprocessing have very similar syntax, which is kind of nice because you often use them hand in hand. So once you understand the syntax of one, you kind of understand the syntax of the other. But again, I'm re-importing threading. I didn't need to in time. And then I've got this function here. And this is the function that will be executed on each one of my threads. And then I have to have a main section. And then I am going to do a for loop that will stand up a thread, 5 threads. So you can see for I in range 5. It's going to have a variable called t, and that t is going to be assigned a thread. And the thread has a target, which is your function that you're calling. You see I don't have the open close parentheses here. You can't do that there. You just say the target function name. And then I have to pass up my arguments, which are like the parameters that you're passing into the function. And it takes a tuple, and it's really annoying because you can't just do a single tuple without the comma, or it doesn't recognize it. So when you're passing it a single argument, you always have to do it like this, where you have the argument, comma, and parenthesis. It looks dumb, but that's just what it requires. If you had multiple arguments, you wouldn't have to have the comma at the end because it would recognize it as a tuple. So if I was passing, 2 parameters look like this. But I'm only passing 1 parameter, and so it has to look like that. So each time through this loop, it stands up a thread, and then it sets up a thread, and then once it gets the thread set up, it starts the threading process, which means it will execute. It does it 5 times. Each one of the threads runs independently, and you can see each one of the threads will just print a result. So I've got 0, 1, 2, 3, and 4. Because the first thread got the number 0, and it was told to print the number. Okay, and this looks ugly, and we'll fix that in a little bit. But I'm kind of glad it did that, so you can see one of the issues that you can run into when you're doing these things. Okay, that's probably the most basic example of a thread. Again, this is totally unnecessary in this case. You don't need to set up threads to print 5 numbers, but it's just showing the process. Okay, so this next one. This time I'm gonna show that issue that you just saw. I wasn't sure if it was gonna show up the first time, but this time I've got a sentence, and I said I want this to end up looking like a nice sentence. That's the items in my list. Goes off the edge of the screen a little bit, and then I'm gonna stand up a thread for each one of the items in my list. So I end up with 1, 2, 3, 4, 5, 10 threads or something like that. And then it's the same thing as the previous one. So I create a variable, and then I assign it a thread with a target of my function right here. And then I pass it my arguments. And in this case, I'm passing the word in the sentence. So that gets passed to that thread, and then the thread starts, which just takes that word and prints it with a space afterwards. So I assume this will look ugly the first time. You can see that I get I want is stuck together with 2 spaces, this to end up looking like a nice sentence. So what's happening here, and this is something you have to be aware of when you're working with these things, is I have 2 threads attempting to access my print function at the same time, and they're mucking each other up. So you end up with weird outputs like this. And if you end up with weird outputs like this, it makes testing difficult, it makes debugging problematic. So we have to protect against these kind of things in scenarios like this. So in that case, we can use what's called locks. And a lock puts a control around an action that you're attempting to do to prevent something else from accessing that action until you're done. So in this case, I want to protect my print statement from other threads touching it before I'm done. So this is the same example, except I've got a thread locker in here that I set up. So I have to still import threading again, and I'm going to create a variable called print lock, and I'm just really assigning it to make it look nicer, threading.lock. So same as before, same sentence, start my threads, but this time I'm going to do with print lock, which is a threading.lock, print the word in the end. So as soon as it starts this, one of the threads starts this process, the other threads have to wait. They can't touch it because it's locked. So they will just stand by and wait for it to complete. And once it's complete, that lock will be released, and then the next one can grab it and lock it. And so in the end, I end up with a sentence that looks much nicer. And technically, this is only working in the right order by chance, but because the words could end up in any order because the threads are all running independently. But in this case, I'm protecting that print statement from other threads. Go ahead, Spencer.
Sure. So I'm having a little bit of kind of a tough time wrapping my brain around this stuff. So
okay.
To me, this kind of seems like, so you have, I don't know exactly how to describe it. Like, to me, this seems like this would wait for every process to complete. Can you like kind of explain how this, like, so if you have a lock on something, how and maybe this is with the print statement, it's actually just going all the way through right away because it's a simple example. But like, is that what's happening here? Is that it's actually just, it's going all the way through, like it'll go through I, go through when, go through this, and then stop? Or is that, or like how is the locking mechanism working here? Can you go a little bit slower on like how it works?
Sure, absolutely. So okay. Again, this is kind of a convoluted example or a contrived example. If I had a more complex function, I wouldn't need to lock the whole function, and I wouldn't want to. I would just be locking the portions where I am attempting to touch a shared program resource. Because if I have multiple things touching a shared resource, I can get weird results. Well, the print statement is a shared resource, so I would want to lock that. It's just in this example, unfortunately, the only thing I'm doing is printing, so that's kind of pointless, right? You are correct, because the only thing I'm doing in the function is printing. I'm essentially enforcing a one at a time type process, and that doesn't do us any good. Now, the next example I'm going to do is much more real world, but there are certain processes that you want to lock. Print statement's one. If you're using what's called pipe, which I don't know if that's in this week's module or the next module, but if you're using something like a pipe, you would have to lock the pipe from having multiple things entering and exiting the pipe at the same time, things like that. It's not the whole thread. It's not the lock isn't locking the entire program. It's just locking access to that one function within the program.
Okay, it's just, lock is only locking print.
Yes, in this case it is only locking print, but it's the only thing the thread's doing, unfortunately.
Okay, that makes a ton more sense. Okay, cool, no problem, perfect, cool.
Okay. Well, and I can try maybe another way is if I had a shared list. In this case, I don't have a shared list because I'm creating the threads with one item from the list at a time. But if I had a shared list and every thread was attempting to read from that list, I would want to lock the read of that list as each thread grabs something, because otherwise two things might try to grab the same word or maybe write the same at the same time. So there's those kind of things. Anywhere where I am reaching outside of my individual thread and using a shared thing, a shared resource, a shared variable, a shared anything, I need to just put those controls in place, because the threads are all working independently and they could hammer on each other.
Okay, let me ask you, and I'm sorry for getting off topic a little bit. So let me ask you this: let's say you had a list of like odd numbers and even numbers. Now, necessarily with locking, and you were feeding it into a lock with this. Necessarily with locking with that, let's say you had 1, 3, 5, 7, 9, and then 2, 4, 6, 8. would with locking, would it guarantee that you're going to go 1, 2, 3, 4, 5, 6, 7, 8 as your outputs then, or is it sometimes going to print like 1, 3, and then 2? Like, does that make sense as well? Will it print them in order?
They're all running independently. You will not get them out in the same order.
You wouldn't. Okay, cool.
By chance, you might, but okay. There is no control over thread order.
Okay.
You could come up with a way, like you could create some kind of a counter that they could utilize to protect the order of things. But oftentimes when you're working in a parallelized setup like this, you're kind of giving up on that sequence of events. So again, we're going to show a real example here, and I'm going to show that it comes out in different orders if you do it 2 different ways. The gain is that you're running really fast. The disadvantage is that you don't have the same level of controls like that without having to put a little bit extra work in. Let me go over this next. I think the next one is the big example, and if it still doesn't help you see it, then we can talk about it some more.
Sounds good. Cool. Okay.
So I love my Starlink stuff. So a couple of weeks ago, we called the Starlink endpoint and pulled down we made 25 calls to pull down a bunch of information to process and make it look nice. Well, that was a lot of waiting in that process, right? We were doing it sequentially. We were making a call, getting a response, making a call, getting a response, et cetera, et cetera, et cetera, until we got all our responses, and then we processed it. This is a perfect example of something that you would want to thread. So this time, instead of doing 25 calls, I'm going to do 50. And first, I'm going to show how long it takes when we do it in sequence, and then I'm going to show how long it takes when we thread the process. So first, I have to do this. This is that first chunk where we grabbed the list of Starlink IDs because we wanted to be able to call the information about each one of the satellites. So nothing's changed there. I'm just gathering that information. And then this time, I'm going to grab the first 50 satellites in that response. Last time was 25. And now, I'll just print this so you can see what I've got so far. It was a few weeks ago. So essentially, I've just got IDs for each one of the satellites. And now I can make a call for each individual satellite. And I'm going to do all 50 of these. So this is the original setup, and I'm using this. This is a really nice thing that comes along with Python. I know you can do it other ways, or I'm sorry, a nice thing that comes along with Jupyter Notebooks. You can do it other ways in like PyCharm or other tools. But what this does is it will just time how long the cell takes to run and give me the output. So from the execute to the last code being complete in this cell, it'll tell me how long it takes. So this is the same as before. It's going to call for each one of the satellites, and then it's going to just store it in a variable, just like what we did before. If I'm going to run this, I think it takes about 12 seconds, typically. Of course, there's some variability in that. Because it's call, response, call, response, call, response, call, response. Okay, so it took about 12.8 seconds to make 50 calls. Let's set some threads to do that instead. I'll come back to this cell in a little bit. This is just printing the output. I'm actually going to print it because this is what we got the first time, and I'm going to come back to that in a minute. Okay, so again, I'm going to time this cell. I am going to do another lock here. I'm going to call it variable lock. And then same as before, set up my empty dictionary. And then I'm going to skip down here. So I'm going to say for each one of the identifiers in that list that I created, or that dictionary I created before, I'm going to create a thread. So I'm going to create 50 threads all at once. And then I'm going to start each thread as it's created. And what the thread's going to do is it's going to take one of the Starlink IDs, because identifier, identity, whatever I want to call it, is being passed along with the thread. And it's going to make a call for that individual Starlink ID. And then I'm going to use variable lock because I am going to be loading this into a shared list. So it's that same process. I can't remember if it was a list of dictionaries or a dictionary list. It's one of those two. But this is a case where I have 50 threads all working somewhat at the same time, and each one of those threads is writing back to a shared collection, either a list or a dictionary, I can't remember. And I want sure that I don't have two threads attempting to write at the same time, because I'm going to get jumbled up results. So I need to lock the writing of that. Well, I think I locked maybe I locked more than I needed to here, but I was locking the JSON JSONification of the response, and then the load into the share collection. It's a dictionary. I see that, and then I release it once it's done. So this is going to give me the same output as I did last time, but don't blink, because it takes 0.2 seconds to complete, whereas when I was doing them in series, it took 12 seconds. So that's a really significant improvement in wait time, because I'm not sitting around waiting for the response for each one. I'm just firing off all 50 calls, and then I'm just going to gather up those responses as soon as they come in. So my program can run significantly faster if this is what is the constraint for my program running quickly. I mean, I've gone over this several times because I'm actually surprised at how much of an improvement this is. Of course, you always need to consider this. If I did this, let's say 5,000 of these all at once, I'm probably going to get blocked by the endpoint, because I'm going to look like somebody that's doing like DDoS attack on them or something. You know, one computer sending 5,000 requests all at once is going to look pretty bad. So you have to be considerate of those kind of things. You know, maybe I would do chunks of 50 like this and get those responses, then do more, something like that. But the point here is that I'm taking out all that sitting and waiting time out of my program by just doing them all at once. Does that make any sense? Hopefully see some value there. The web scraping is even more significant. We did web scraping a long time ago. I didn't want to try to bring that back up again here, but Craigslist pages, there was a lot of just, you know, pulling in data, processing, and et cetera, while you were sitting and waiting. You could definitely thread that out. You know, maybe you scrape each one of the categories independently, and then you have all those results brought together at the end, making a much higher value output. Okay, anybody have any questions? Because I'm glad to go over anything again here. Otherwise, if on the next slide I go to, I think I have some warnings here. Oh no, sorry, I had one more thing I wanted to show you. So a couple of slides ago, this is where I wanted to put this. This is the response from sequential run, and you can see it starts with Starling 30, let's say. When my output again now doesn't. Starling 23. There's randomness brought in here. Whichever thread gets back first is going to get written first to this shared object, or this shared collection. So I cannot guarantee the order I sent is the order I'm going to end up with in my output, unless I put some other some kind of overhead counter or something, or an identifier that I bring along with it, so that I can resort the output. So that's something you need to be aware of. You can get completely jumbled up order in the process of trying to get results faster. And in this case, it doesn't really matter, because what I was doing here was trying to pull data about Starlink, so it doesn't matter which one came back first. Okay, so as I said, that's a significant speed improvement. A couple of drawbacks we need to consider. There is overhead with using these threads. Your processor is constantly jumping between the different threads, trying to keep everything in order. So if you are in a scenario where the threading process doesn't give you significant improvements, you may want to consider not doing it. Again, and as well, it brings along complexity. Not everybody is aware of how these things work, so when you're trying to work with somebody else that may not be aware of it, there may be difficulty there for them understanding it, as well as just yourself stepping through your own programs can be a little more difficult if you're not comfortable with it. So you want to bring those considerations in when you use threading, as well as multiprocessing, which we're going to go into next. Okay, I'm going to switch over to multiprocessing then. So threading was kind of faking that parallelization, right? We're still using doing a single thing at a time. We're just bouncing back and forth between different threads. Multiprocessing is true parallelization on different processors. So some of this depends on how many processes your computer has. And I show a thing at the end so you can figure out how many processors your computer has. This one that I'm working on has 12. So I could set up 12 separate processes to run concurrently and then take the result of those processes in my program. You can tell your program to do more than 12 processes, even if you have 12 processors, but you don't gain anything. So it's something you want to be aware of. And I'll show you again how you can tell how many processors you have to make that a little bit easier. As I said at the beginning, Python only runs on a single processor. Multiprocessing lets us set up instances on our other cores. And if we are attempting to process something that has a high CPU usage, we can break up the work between the different instances. So here is a process that doesn't really have any value, but just to show that I'm going to use multiple processors. You'll notice that it looks exactly like threading, and it's because the two modules are very similar. So for I and Ray5, I'm going to do a multiprocessing process, and I have a target just like I did before. And if I had arguments, it would be the same as what it was with threading. I would have to do comma, args, equals. If it was a single argument, same thing as before, where it's if I had an argument. And you always have to put the keyword names in this, which is kind of annoying. Args equals, if I'm passing the number 5. If I had a single argument, I would have to do that again with that comma at the end. But I don't have to in this case. That, and I can run it, and you can see that it will. One of my processes just kicks out the word test. So nothing super exciting, but I did stand up 5 processes on different CPUs to write out the word test. Now this is a little weird because if process number 1 finishes before process number 2 starts, you actually won't stand up a separate processor. It'll just keep feeding it to the same one. So this case, although visually it's the structure's right here, I'm probably only working on a single processor because my Python program can kick out the word test before it's going to be capable of standing up another processor. Okay, but I just wanted you to be aware of that. But I've got some other examples here that will help. Now, this is also the point where, unfortunately, there is a limitation or kind of an annoyance in cheaper notebooks, where if I have to have, and this only affects multiprocessing for some reason, if I have to send in arguments like this to a target function, I can't have the function in my program. It has to be a separate Py file. I do not know why that is. It's annoying, and I'm going to show you in some other examples where I actually set it up that way. But in this case, I'm just going to copy this over into PyCharm and do it because PyCharm doesn't have that same limitation. So I'm going to grab this, and I'll talk through it here. Okay, so before I run it, again, I don't need time right now because I will need time because I have a sleep in here that I've got commented out because I'm going to show this a couple of different ways. So again, I've got a function I'm calling spawn, and then I'm going to attempt to create 25 processes, or what it will do in this case is it will access all of my processors that are available and keep trying to feed it these different function runs if it doesn't finish before the first time. So for instance, if I had a really complex function, it would spread it out among all 12 processes and then wait while those processes complete. And if one of the processes completes, it will then send in another function run to run. So it will just max out the amount of processors that I have available and try to run it as fast as it can. All of that stuff comes along with the Beret to make this a little bit easier. Now, I can limit the number of processors I use, which I will show in a little bit, but the way this is structured, it will just attempt to use all of my processors to get this done as quickly as possible. So, so again, I've got processes. And then, okay, so I create a list here where I just store all my jobs. I'm not sure why I was doing that. I must have been messing around with something. But I created this object P, and then I appended it to this jobs list. And then I start the process, and it'll run all of them. I don't know how quickly. This should run pretty quickly. It's just a number. So you can see there, I sent it the numbers from 1 to 25, and then it printed the number, and I get them back in that completely random order like we've been talking about, because whichever process finished first is the one that came back first. Now, I've got a couple of things commented out here, but first I want to just do this, because there's a good chance, again, that this probably just ran on one processor. But let me take out my time.sleep. I have random. That should give me a wait for 0 to 1 second, if I'm not mistaken. So if in this case, I think I have a better chance of standing up multiple processors. Let me do 2 times. That's still not enough. I'm just inserting a slowdown in each one of these processes to act like it's a more complex scenario, which it really isn't, because I'm just printing out a number, but I'm just making it wait so that it will actually spawn the separate processors. And let's see if I can get it to show up in my process monitor. I put a link to this product in Blackboard. What Process Monitor does is it allows you to have a more controlled view of what processes information is showing. So it's not super easy to use. You people on Macintoshes are kind of lucky. Your regular activity monitor allows you to filter. Windows, unfortunately, does not, which I find rather annoying. So you have to use this third-party thing, and then you have to set up a filter. This tool is kind of a pain, but what I wanted to show here is as I run this program, you'll get to see these different processes start. So if I run this again, you can see in this case, each one of these is a separate process being created with a different process ID. So this is my program is executing multiple Python.exes, one for each one of these processes that I'm trying to run. So it's spreading out that work across multiple processors is what I'm showing there. I show another example here in a little bit, but just kind of trying to let you see that it is truly at the system level spreading out this work. Okay, so that's that. Let me see what my next example is here. Maybe it can help a little more. Oh, I wanted to talk about this. So right here at the bottom, I have p.join. What p.join is a blocker, and it is an intentional blocker. And what it says is, do not continue with the program until this process has completed. And that's, in this case, I don't really want to do it because it would do it for each one of my processes, and then it would kind of ruin the purpose of it. But this is important because if you send off a process to run, and then you continue with your program, and it's looking for a result from that process, and the process isn't done yet, your program's going to crash, or it's not going to do what you expect it to. So what this does is it's a stop point that says, at this point in the program, do nothing until that process completes, and then we can continue. So it's pretty important if you're trying to bring back data together to your main program. You need to put these joins in. P.close is kind of unnecessary, but because it's kind of a quick garbage collection thing where once the process is complete and you don't need it anymore, you can close the process, which kills it off. But your program ends, it will also kill off the process. But it's something to be aware of. So I don't need it here, so I just left it commented. But in this case, I'm going to do this one. I actually have set it up the other way. So this is where I'm making Jupyter Notebooks work. You can see I have this import counter as C. That's another program in the same folder. Let's see. Am I in the right? Nope. I've been working on the next module. Module 12. So I've got this Python program called counter. This is what it's accessing. So when I run this program, it's going to do, first I import OS. and a submodule called getPID. And so I can see which process IDs are being assigned by my operating system. And then I am going to bring in the sleep module, and because I want to intentionally make this take a moment and sleep, and then I'm going to, in the end, I'm going to output the PID, and you'll see this run so you can understand what I'm saying. But so it's going to, I've got two, this time instead of doing as many processes as possible, I'm kicking out specifically two processes. So the first one is going to call my function, c.counter, and it's going to pass my empty dictionary. Oh, my manager dictionary. So this is, when you set up a manager, it's like a, kind of groups all this stuff together. So anyway, so I'm going to pass it an argument, and then I'm going to do the same thing with the other one. So I'm passing it my empty dictionary, so both of my processes can work on this dictionary. And then it will start them, and then I will wait for it to join them, and then I will print my output dictionary. So this is important, the join here, because otherwise I might print my dictionary before the data's been written to it. So this time I need my joins. So if I run this, oh, I should have cleared my process monitor. Hold on. Oops, there we go. So that program's running, and it is creating my threads. Hold on, I went to a different slide. You can see I stood up two threads that the dictionary output after the processes were done was PID. I'm sorry, I shouldn't say threads. I should have said processes. 24788 and 1564, and I can see those here. 24788 and 15640, just showing again that it is creating these two separate processes to run independently. I think I do this next slide, which is kind of pointless. I do it. I send out 8 of them this time. So I'm purposely creating 8 processes to run. So it's the same thing I just did. I don't know why I have that in there twice, but it's the same thing except across more processors, and then I'm joining them all together. Of course, I've got that wait function in there that's slowing it down intentionally. That's why it's taking a moment. I gotta wait for this to finish. So again, that's kind of the same thing, except I do it across more processors. So I've got 10 of them going this time. Okay, so that's just showing it, spreading it out among your computer's crunching power. So to get my multiprocessors to communicate properly, I could pass them a dictionary like I did, or a list like I did, but the proper way to do it is using either queues or pipes. So a pipe and a queue are very similar. They are exactly what you would think they are. I'm able to put items in one end of the queue and then read them off the other end of the queue. So it's by default, it's a first in, first out process. Same thing with pipes. You put things in one end, and out the other end, you can pull them off. So each of your processes or processors or multiprocesses can feed into that queue as they get data figured out, and then you can read it out the other end from your main program. The advantage of queues, it already has the locking functionality built in. So one process writes to the queue at a time. It will not let another process attempt to write to the queue while a different one is. So it's the traffic cop for you. It controls all that. Pipes don't do that. You would typically use a pipe if you only have one thing putting data into the pipe and one thing pulling out of the other end of the pipe. And really, the advantage is that it doesn't have the overhead of all of the thread locking or pipe locking or whatever. So it's faster. So if you are literally setting up something where you're writing one thing and you're reading on the other end, you would use a pipe, but otherwise you would typically use a queue. I'm going to use for the rest of the demonstration here because it takes care of all that locking for me. Okay, so I got to do this one PyCharm. I stole this one from this YouTube video here, but I'm going to bring it over and then we'll talk through it. Okay, I got to get out of this view to even copy it. Maybe I shouldn't say stole, borrowed. Borrowed distribution. So it's probably pretty small. So I'm going to import, for multiprocessing, I'm going to import processing queue. I'm going to use the multiprocessing queue. I've got two functions that I'm going to be. One just takes the number that's sent to it, squares it, and then puts it in the queue. And I have to pass the queue as a parameter as well, because otherwise the function won't have access to the queue. The other one does the same thing except it cubes it. So I send a number, and I send it the same queue, and then it cubes that and puts it back in the queue. Or cubes it and puts it in the queue, not back in the queue. It cubes it and puts it in the queue. And then at the very end of my program, I'll read the queue. So you can see here, I'm going to create a range of numbers, and I'm going to create my queue, just called queue, because I wasn't being super creative, or whoever wrote this wasn't. And then I'm going to create a process called square process, which targets the square function, and I'm going to send it my numbers in my range, and I'm going to send it my queue. Same thing with the cube process. It's going to be called cube process. It's going to target the cube function. It's going to get that same set of numbers, and it's going to get that queue. I'm going to start both processes, so square process, cube process, and then I'm going to join both. So that means my program will wait until both of those processes are complete before moving on. And then this is a good way to read everything off of a queue. So you can do while not queue.empty. So it will just repeatedly read until it gets to, I can't remember what the error is, but it gets a specific error when the queue is empty, and then it will stop the while loop. So it'll just read everything off the queue and print it. Anytime you get something off the queue, it moves it from the queue. Just maybe it's obvious, but I'm just going to say it just to make sure. So if the number 5 is at the end of the queue, you grab the number 5, it is now automatically off the queue. You don't have to like delete it or anything like that. So when I run this, oops. You can see I get 014916 and 0182764. So these processes were so simple that one really finished before the other one even started. But I was able to run them independently, put them into a queue, and pull them off the queue in my main program. That's what this is attempting to show. Okay. There's one other thing I want to show you. Is there any questions on that so far? This is something that you'll have to play around with and get comfortable with. Go ahead, Spencer.
Sorry, me again. I was wondering, I don't know if anyone else is kind of struggling with the same stuff. Could you go back through kind of slow on just line by line what is happening and like what's contributing to it? In particular, in like the name equals name section.
I'm sorry, can you say that again?
Yeah, so like in the
part of it?
In the name equals name section, can you kind of walk? You stepped through it already. Could you go a little bit slower and just, line by line what's happening and like what's going?
So is this the one you're talking about, Spencer? Where I stepped through it in PyCharm, or is it one of the other examples?
Yeah, the PyCharm one. Yes, and then just like starting on numbers equals range 5. You were explaining it, but it was a little for me. It was a little fast.
Okay, fair enough. Let me do this. This is what I do when I'm trying to understand what's going on.
Perfect. That'd be awesome.
Instead of just trying to live in the variable world, let's just actually see. So I'm going to run this just so we can see the output of that range. Okay, so I create a range object. Kind of. I don't like how that looks, but all right. So starting at main, I'm creating a range object, which will give you the numbers 0, 1, 2, 3, and 4. So that's what you get when you do a range of 5. And then it prints it as an object, but I'll read it individually in the functions. This isn't how I would have written this. This is what I get for using somebody else's code. And then I create a queue, which the queue object is what we're going to share among our multiprocesses to write to this queue. And then we'll read from the queue in main. So we need the queue object to be created before our processes start. And then I'm creating a process that's called or it's called square process, so I'm assigning it to a variable called square process. You always have to assign your process to a variable. Sometimes they're throwaway, where you could see I was creating the same process name over and over, but in this case I'm being a little more explicit. There are times when that's kind of nice. Square process, it's going to be type process. It is going to access the square function up here, and then it is going to be passed that range object, and then it's going to be passed my queue so that it can write to it. Queue process does the same thing, except it targets the queue function. So once I hit start on those in line 20, it'll go up here. Both of these will be running independently at this point when I start both queues, or start both processes. And it's going to go through my range object. It's going to for through it, so it'll say for first item in range, second item, third item. So I will become 0, then 1, then 2, then 3, then 4. And for each one of those iterations through the loop, it's going to put the square of that number into the queue. Queue will do the same thing. It's going to take those 5 numbers in that range, 0, 1, 2, 3, 4, and then it's going to iterate through a for loop each time. So it's going to be 0 cubed, get put in the queue, 1 cubed, get put in the queue, 2 cubed, get put in the queue, et cetera, et cetera, et cetera, until it runs out of numbers. Then that function will end and that process will complete. I'm putting the join here to make sure if I didn't do this here, I could try it just to see what happens. I'm probably going to get a weird result because the square process will finish so quickly that it will attempt to read from the queue before the queue. I haven't tried this, but it's probably going to be weird. Yeah. So what happened is my program ran so fast that there was nothing on the queue by the time I tried to execute this code. So it said queue is empty and then ended the program. So this is that checkpoint where I'm forcing my program to just sit and wait until all these things are done, and then move on to actually reading from the queue. So it's something you need to be aware of. Things run super fast on your processor, so your program can run quickly, quicker than what you, I guess, would think. I would have thought something would have gotten written beforehand, but I guess not. So this time I put those joins in there to stop the program from running, and you can see I get my output. And I get it in kind of a random order again, because it depends on which queue runs faster, or which process runs faster. Okay, does that help? Is there any specific thing I need to speak more to in that particular example?
So that did help a ton. Yes, absolutely. The one section that I think I'm struggling with, and I don't know if no one else is, then maybe we could just talk about it. But if you go back to like the square process, the processes section. Yep.
Yep.
Yes. The argument section I think is where I'm struggling. So can you go back just over that once more about what is happening there with like what's getting passed and how that's layering? And would there be a possibility if you don't have arguments in a function, is there a way to make that work still?
Oh, sure. Okay, so if you don't have any arguments, then you don't even put that parameter in. So there wouldn't be anything passed into the process. If you have a process that was running completely independently, you could just start the process. You create the process and start the process with no arguments. Maybe this would help. Let me pull this down a little bit. I got things zoomed in to try to make it easier. What I'm doing here is the equivalent of, let's see, square numbers queue. This is a normal function call, right?
Yes.
That's all I'm doing here. It's just the syntax is different.
Okay.
I'm running a function that takes 2 input parameters.
Okay.
It's just the way they do it. I don't know who wrote it, but this is the way they do it. The difference between this and this is that when I do it this way, it's putting it out into its own processor to run independently.
That makes a ton of sense. Okay, so you just have one processor for square and then one processor for cube.
Yeah, and again, behind the curtain, they might be running on the same processor because they're running so fast. But if it was two complex processes, the library will take care of spreading out to the processors as it needs to. So
Okay.
I don't want to say I guarantee they're on a different processor because I can't, but I'm saying that it is giving the program the ability to do that by doing it this way.
Okay. That makes a ton more sense. I think where I was getting hung up was I thought that like each line, the square process and cube process, was going to break down each function into separate processors. So actually what it's doing is each line is executing on a different process, or on a different processor.
Yes, in this case they are. I'm going to show you a pool which works a little bit differently here in a second.
Okay, sounds good. Thank you.
But yeah, in this case, I am specifically assigning them to run as independent processes that the library will decide if they need to run on a separate processor. Okay. All right. So let's keep going. And I like these questions. I'm glad it's being asked. I think these are powerful libraries, but they are difficult to get comfortable with. So either now is the time to ask questions, or you can email questions, of course, as always, or hit me up at office hours. But I want to be able to make this as clear as possible. Okay. So pools versus processes. So this is the last kind of big thing I wanted to show you. With multiprocessing, there's kind of two ways to do it. I guess I could put this back into big view mode so it's a little bit easier to read. A pool is you have a simple task that you're running a whole bunch of times, and you're just kind of letting the library spread it out to X number of processors and do it as it pleases, where it will just, as quick as one process completes, it'll fire off another instance of it over and over again until all of the work is done. I'll show an example. A process setup is like what we were just doing, where you are specifically assigning a process to run on a specific function. So it's more you're deciding how it's assigned and what it does. A pool is, let's say, you have the same function that you need to run 10 million times. You would do a pool for that. You would just let your computer run that in parallel as quickly as it can and get it done. A process is like I just did, where one of them is running a square and the other one's running a cube, right? You need to have a little more control. So you need to be more descriptive, or I can't, the word's not coming to me today, but you are telling it exactly what each process needs to do. So a pool, in this pool, I'm going to square numbers, and then again, I'm spreading the work across multiple processors, and I threw in a 5 millisecond wait on each process because otherwise things happen too fast. So I'm purposely making this thing slow down. So I'm re-importing this. I'm giving it a name this time to shorten it up as MP. And then this is a tool that you can use to figure out how many CPUs your computer has, which is kind of nice. So you can see this particular computer has 12 processors on it. So that helps you who are determining how many processors you have available. If you're specifically stating, I want to do this on 4 processors, you know you at least have that many. You can actually use this as your parameter as well, and it'll just max out the number of processors available. But that's just prep work here. Okay, so here's where I'm actually doing the code. Yeah, so again, I'm doing this in Jupyter Notebooks, so it has to be a separate function. The workers function is exactly the same as what I have in this commented out code. I just had to do it as an independent thing. So I wanted to show you what's actually in the, well, I guess I can just bring it up on the screen, but I have a separate program called workers, and you can see, oh, I threw the sleep in there. This is all it does. Just sleeps for 5 milliseconds and then returns the square of whatever is sent to it. So in this case, I am going to specifically assign number of processors as 1 the first time. This means I'm only going to run on a single processor, which means I'm going to get no gains from the library or from the multiprocessing. And then I'm going to create a pool with this many processes. So I'm saying I wanted to have 1 process because I'm assigning the variable. I could have just, if I wanted to, I could have just put the number 1 here, but whatever. So I'm saying I want to run many processes, or this many simultaneous processes would be another way to say it. And then I'm going to use mapping. And I know it's been a long time since we've done mapping, but this is the syntax that you typically use if you are doing pools. So I'm going to use workers.worker, which is the function, right? That's this. And I'm going to send it I for I in range 0 to 10,000. So each time it runs, it'll take the next I as the variable. So if I had 10,000 processors, this would just run all 10,000 at once. But I'm saying I'm going to only run it in this case one at a time. So it will create a process to run it 0. So it'll square 0 and get the return and assign it to output. Then it will get 1. It'll square to 1, and then it'll assign it to output. Then it'll 2 and square it and output, et cetera, until it's done all 10,000. And this should be pretty slow because I am using a single processor. I don't actually remember how long this takes. I think it's something around 50 seconds, something like that, because it is just running it in sequence. It's doing one process, completing, doing another process, completing, doing another process, completing, et cetera. And I've got the timer going as I did before. Sometimes it's good to have like a some kind of an indicator that your program's still functioning. Like you could have it print dot or something so you know that it's working. But I had this working, so I'm sure it'll go. Okay, maybe I should have done an easier example, but I think it's something like 52 seconds. This sometimes happens when you're working with large processes. You're not sure why it's not complete yet. You're waiting and you're waiting. There we go, 55 seconds. So it ran all 10,000 squares with, remember I put that delay in there to make them take longer. Normally it wouldn't take your computer that long to run 10,000 squares, obviously. You'd probably do it in the blink of an eye. But I put that delay in there to slow it down so we can show the value of having multiple processors. So your thought process would be, well, if this is a more complicated math problem, maybe I'm trying to figure out sum of squares or something like that, and that's a little more complicated, something like that. But this time I'm going to give it all 12 of my processors. Whoops. Or I could have just said, oops. I could have just literally just stuck this in here, which I could just do, just to show. Oh, stop that. I could just stick in, because that'll resolve to 12. It's the same thing. But the good thing is that if you set up something like this and you have to share your program with another computer, that computer will maximize out the available processors. Again, if you do more than the number of processes on the computer, you just don't gain any performance improvement because it can only spread it out across the amount of processors that you have. Let me do this. I'm going to clear this thing again so we can see it running. So now I'm going to run it with all 12 processors. You can see it's created all those threads for me. It's chunking through the numbers as quick as it can. And in this case, it took 6 seconds instead of 50 seconds. Now, again, this is a contrived example, but you can see by doing it in parallel, I have spread out that workload among different processors, so I can hopefully run my program more quickly.